Like a lot of aspects of this course, calculus comes into play with a lot of the different types of functions. So we've learned about inverse functions and inverse trig functions. And what we want to do now is apply calculus to those. So derivative calculus and integral calculus. So we're going to do a proofs of what the derivatives of trig functions are. We're going to treat it like we did with log functions. If you remember how we showed the derivative of a log function, we're going to do the same thing with the inverse trig function. So, for example, if we let y be equal to inverse sine of x, so x could be equal to sine of y. And remember our range for y must be between minus pi on 2 and pi on 2. So the derivative of x with respect to y is cos y. So when we do that then, cos y would be square root of 1 minus sine squared x. And we get that from sine squared y plus cos squared y is equal to 1. And remember that we just defined sine y to be equal to x. So dx dy could be written as the square root of 1 minus x squared. So dy dx is 1 over square root of 1 minus x squared. So there's our derivative of sine of x, inverse sine of x. So there's the proof. Have a look through, and we can do this because cos y has to be positive because we're in the first and fourth quadrants. So if you go, well, why don't we take the positive square root? That's why. Y is going to be in the first or fourth quadrants, and so if that's the case, well, cos of y is going to be positive. And that shows the same thing with the next one, where we do the derivative of cos of x. So we let x be cos of y and derive that. So we get minus sine of y. So we're going to have between 0 and pi. So again, because it's in the first or second quadrant, sine of y is going to be positive. So we get the situation where we've got sine of y is going to be, can be written as square root of 1 minus x squared. And so dx dy would be minus of square root of 1 minus x squared, because we had it as it's going to be because it's going to be positive there. So in that case, we get dy dx is equal to minus 1 over the square root of 1 minus x squared. So that's the derivative of cos x. So there's the two you have to remember. So inverse of cos x is minus 1 over the square root of 1 minus x squared, and inverse sine of x, derivative of that would be 1 over square root of 1 minus x squared. So all the difference is the negative. For tan, well, we go this way. Let x be equal to tan of y, and so dy dx would be the derivative of tan of y would be sec squared y, which could be written as 1 plus tan squared x, tan squared y, which tan of y could be written as x, because that's what we defined it as there. And then we take the reciprocal of that, would give us 1 on 1 plus x squared. So there's our derivative of inverse tan of x. So there's the proof of those rules, and they're the ones we need to remember. In general, that's the case where it's just x. If we've got a function there, well, it doesn't do too much difference, except we get the derivative of the function over the square root of 1 minus the function squared. If it's inverse cos of x, it's minus of that. And if it's tan of x, it's the derivative of the function over 1 plus the function squared. So there's the rules. So they're ones you're probably going to use more. So they're the ones you're going to have to commit to memory and keep in place to do the derivatives. So let's look at examples. 2 lots of inverse sine of x. Deriving that, well, that would just be the 2. It's not going to make any difference. Derivative of inverse sine of x is 1 over the square root of 1 minus x squared. So 2 over the square root of 1 minus x squared. Tan of 3x. So that's going to give us the derivative of 3x is 3 over 1 plus the function squared. So we're using this rule. So you've got to keep remembering that rule and keep applying it. And 3x all squared is 9x squared. So there's our manipulation, and there's our result. Find the derivative of inverse cos of x minus 2 to the power of 5. Well, again, all our rules apply as was done before. So this one would be a case of let's apply the chain rule. So 5 comes down inverse cos of x minus 2 to the power of 4, so because we subtracted 1 from the power. Derivative of inverse cos is minus 1 on the square root of 1 minus x squared, and the derivative of 2 is 0. Leave it like that. That's all we need to do. Question 4, again, e to the power of inverse cos of x while deriving an an exponential function. Well, we're going to have the exponential function times the derivative of the function itself. So we're using the rule there. So e to the function of x, derivative of the function times e to the function. So 1 over the 1 square root of 1 minus x squared times e to the inverse cos of x. And that's all. That's as simplified as we can write it. First and second derivatives of this one. So derivative of tan x, inverse tan of x is 1 on x squared. And I'd put it as a power of minus 1 to apply the chain rule to do the second derivative. So we bring the power down, I'd subtract 1 from the power, times by the derivative of the bracket, and that's where we get the minus 2x on 1 plus x squared all squared. And then we can start to apply these rules to other applications we've had, like to find the gradient of the tangent. So we know that occurs when we get the first derivative. So the first derivative of 3 inverse cos of x is minus 3 over square root of 1 minus x squared. And when x is equal to a half, we're able to put that in and find the gradient. So we substitute it in and do our calculations, and we come down to, if we're going to find it exactly, it'll come down to minus 2 root 3 doing all our surd work there. Or if we want, if you want a decimal approximation, you can get a decimal approximation as well. That would be okay. The next one, again, hit gradient of the normal. So if we remember the gradient of the normal, we find the gradient of the tangent, and then finding the negative reciprocal of that. So we get the derivative, substitute 0 in, we get a gradient of tangent as 1, gradient of the normal must be minus 1. That works out rather nicely. Equation of the tangent, so we've got our point, so we find our derivative of 2 inverse tan 2x, which gives us 2 times the 2, 1 plus 4x squared. So we're able to get that function, substitute a half in, and that gives us a gradient of 2. So we get our gradient of 2, our point of a half pi on 2, and sub it in and simplify it down to an equation of a line. And there's our tangent. This time we want to find a few things involved. We want to sketch it, we want to find domain and range, and find the gradient. So again, substitute 0 in, we get, when x is equal to 0, we get minus 3 on 2. Sketching the function, well, we know what a cos function looks like. It goes from 0 to, will normally go from 0 to pi. Because it's x on 2, it's going from minus 2 to 2 in our domain, and our range is increased by 3 as a multiplication factor of 3, so it's going to go from 0 to 3 pi up there. So then we can write the domain and range of the function. You could have done that beforehand. So there's your domain and range, as we just said. And then find the gradient of the function. Well, we derive our function there, substitute 0 in, and there's our gradient of our function at 0. And question 10 here. This is an interesting one. Let's have a look here. For the function here, find the derivative. So we get the derivative of this one. We get 1 over the square root of 1 minus x squared plus minus 1 over the square root of 1 minus x squared. That's going to give us 0. What does that indicate? Doesn't matter what the value of x here, the gradient of inverse of sine of x plus inverse cos of x will be a straight line, because it's got a gradient of 0. So it's a horizontal line. So what horizontal line is that? Well, it's going to be the same value no matter what you put in. So if you substitute 0 in, or you substitute 1 in, or minus 1, you substitute it in, you're going to get a situation where it'll be equal to pi on 2. We'll put 0 in there, or inverse sine of 0 is 0. Inverse sine of cos of 0 is pi on 2. So it's going to give you those values. So that's an interesting one, that and how it works out. Remember, it's only defined between -1 and 1 because you can't take anything greater than -1 and 1, so it stops there at those endpoints. But any value you put in is going to give you pi on 2. And how do you know? You can't really just keep substituting values in to see that. But how do you know it's not going to change? Because your gradient of your line is going to, it's going to be a line, but the gradient of this function is going to be 0 at all times. So there we go. That's an interesting one. That's popped up in a few exams, and they like that because it's a different type of question in terms, and it calls on the understanding of gradients and being able to draw it with a bit of understanding of the gradients of that function there.